So this presentation is also going to be on the internet, and SK Planet will put a video up I learned, and the slides will be on SlideShares. So if you find interesting information on these slides that you want to look up later, you can always do that on the internet. So what we are doing is creating virtual worlds. And for what we are doing, we want to join film and game in a way where we cannot have sharded worlds like World of Warcraft, where you can have a friend playing in one server and another friend playing in another server, and playing avatars who can never meet. So what we are doing is something that automatically has to do with big data, and that automatically has to do with high-velocity databases. And that is the reason why at a certain point I went on a quest after a project that used Java and MySQL and tried to have a very objective look at what would be the best language and the best database for the next game server that I would be programming. What I came up with was VoltDB as a database and Erlang as a language. And these are both open source technologies that are built for scaling. And I would like now to look at what makes them special, how they look, what does the source look like if you program them, and to try to answer the question, or help you answer the question, if they make sense to use for you. VoltDB and Erlang actually have some things in common. They're both the results of a concrete need of a company that was in IT. They're both made for distribution. It is not like many other products that distribution was added later. They are made for multi-core, like we find now in all commodity servers. And they are both truly different approaches to solutions that we saw before. They are not only made for parallel architectures, but they're also using parallelism to be different and to solve things better than before. Both products have a strong company behind them that is also providing professional support. And both are quite well known in circles that have to do with the problems that they're dealing with, although not everybody knows VoltDB or Erlang. Let's start with looking at VoltDB. VoltDB, one could say, as a rough approximation, could be described as Redis plus SQL plus scale. From a business perspective, the reason to use VoltDB is quite clearly to reduce costs, to be able to scale seamlessly, as we learned this morning in the keynote, and to maintain strategic flexibility. The reason is that the way that data is stored in VoltDB is much less special than in many other databases that have come up in the new SQL times. If you look at it as a programmer, then the reasons are a little bit different. It's more like, okay, not everything about SQL was bad, so let's not throw all of it away with NoSQL databases. Still, you can use the goodness of in-memory that you have probably learned in Redis, and you are using a product where you can later, if you're successful, be sure that you can scale. I would like to describe VoltDB a little bit like the Redis of clusters. I think many of you know Redis probably, and Redis as an in-memory database can do stuff incredibly fast. Just probably it is never going to be a distributed database. There are efforts underway to do that, but the problems they are facing are probably such that Redis will not have transactions when it is run in the cluster. VoltDB, however, does have that. I would also like to compare VoltDB to MySQL. I think everybody here has probably used MySQL at one point or another. And however, the point can be made that SQL in itself has some flaws. In the end, it's about essentially math. It's about relational databases. And that means no matter what the syntax is, there's a lot of sense and a lot of science in how SQL works. And if you wouldn't have queries and only key value access, you might sorely be missing queries at some point. If we look at CAP, some of you might know it, that is a very good tool to get orientation about databases. Many NoSQL databases, for example, are sacrificing consistency and introducing eventual consistency and focusing on high availability and partition tolerance. To just get an orientation, VoltDB is rather on the side of consistency and high availability, even though you can make the point that VoltDB is not really lacking in partition tolerance, and there are some flames going on in the blogosphere about whether VoltDB can claim that it really satisfies all of CAP. ACID is something that is summing up attributes that everybody should probably assume are for granted in a database. Basically, ACID describes that if I store something into the database, at a later point I want to get the same thing back. One should think that's for granted, but it's not. Not even the Oracle default setting is giving you true ACID. MySQL, by the way, is a little better at that. And VoltDB is giving you ACID transactions. An interesting metaphor to think about your problem, whatever it might be, is double bookkeeping. And if I can take games as an example, if you have a very simple game where one player only basically does actions that never really affect another player, then you do not need double bookkeeping. But as soon as you have a game where one player can interact directly with another player, you have to have the possibility to do double bookkeeping. That means, for example, if one player sells a sword to another player, you want to be sure that in the end, the sword has changed hands and the money has changed hands. And do not have a situation where a transaction crashed and you have half of it realized, or have two swords all of a sudden, or no money anymore. If the database does not provide you with double bookkeeping, it is very, very hard to implement that on top of a database that does not provide it. So how does VoltDB manage to be so good? The magic sauce really comes down to compiled-in queries, where you program store procedures in Java that in the end become part of the database engine. Another ingredient that's very important is single-thread execution. I'll explain that in a minute. And the same with snowflakes and clones. What VoltDB does is not very much surprising. It does a consistent hash about the entirety of the data that has to be stored, and then stores the data across several servers. It even does that with added case safety. That means an individual server could crash, and you would still have all of your data. That means that, for example, if the left-hand server crashed, you can take the content from the server to its right-hand side and to the far right, and you would still have a complete copy of the entire data. What it then does is it uses the fact that most real-world data has a Snowflake structure. For example, you could have a customer table at the center of the snowflake, where the primary key in red is the customer ID. Most of the data in your database would, in that case, point to the customer with their foreign keys. And if it's going down the structure, then you would have other tables that would have their own primary key, that had other detailed tables that would be pointing to that dependent table. However, you also always have data that is not part of the snowflake. To stay in our example, for example, the product numbers and the table where you have the names of your products would probably not be part of the snowflake, but in a parallel order. What VoltDB does, it is sharding the snowflakes across all of its servers. And for example, if the hash in a very primitive solution would go on the surname of the customers, then the first server would be storing all of the customers that have A, B, or C as the first letter of their surname. The data that is not part of the Snowflake structure is then cloned by VoltDB and replicated across all servers. And that's a very important, a very genius trick that they're using there. And it makes sure that most transactions you want to do can be done on a single server in a single thread, because you have most of the data available that you would use in most of the transactions that a normal business operation takes. VoltDB is organized in a way that every partition of the data is governed by one thread. One thread, obviously, cannot be in contention with itself. It means it does not need locks against itself. So if you have one thread executing one transaction, that basically means you can have transactions without locks. This is true for each of the individual partitions inside VoltDB, and this is one important key why it can be so fast. I made a benchmark a couple of months ago with VoltDB 2.5 and a Node.js driver that VoltDB Inc. has produced.